Good morning, JVNs. Today we are discussing about the continuity. Continuity means if you precise the path of a ball as an unbroken curve into the precisely mathematically formulation called continuity. Definition of continuity. The function is undefined at C. The limit of fx does not exist as x approaching to C. The value of function and the value of the limit at C are different. These are some types of discontinuity in the graphs. To hold this, and we define the condition that a function is continuous implies a function is said to be continuous at a point C. We provide the following condition are satisfied. FC is defined means if a function is defined on that point, limit x approaching to C, fx exists, and limit x approaching to C, fx is equal to FC. If one or more of the condition of this definition fail to hold, then we say that f is a discontinuous at C. Means if any one of three conditions cannot be held, then the function is discontinuous at that point. Like this, we define a discontinuity. A function like in the figure 1.5.1b, 1.5.1.b means jump discontinuity. Jump discontinuity means the function goes continuous, but at a point C, it will just jump the value, the y is equal to fx, jump from at the point C. This is known as a jump discontinuity. Determine whether the following function are continuous at x is equal to 2. First function will give us fx is equal to x square minus 4 divided by x minus 2. Second, gx is equal to x square minus 4 divided by x minus 2 if x is not equal to 2 and 3 is equal to x is equal to 2. And the hx is x square minus 4 divided by x minus 2 if x is not equal to 2 and 4 if x is equal to 2. In this case, we must determine whether the limit of the function as x approaching to 2 is the same as the value of the function at x is equal to 2. In all three cases, the function are identical except at x is equal to 2. Hence, all three have the same limit at x is equal to 2. Limit x approaching to 2 fx is equal to limit x approaching to gx is equal to limit x approaching to 2 hx is equal to limit x approaching to 2 x square minus 4 divided by x minus 2. X square minus 4 implies x minus 2, x plus 2, and x minus 2 divided by x minus 2 is cancelled, and x plus 2 limit x approaching to 2 implies 4. That means all the limits, all the functions have the limit at 2 is 4. But fx is undefined at x is equal to 2, and hence it is not continuous at x is equal to 2. And gx is defined, but the limit is not equal to g of 2, then which is not the same as the limit. And hence g is not continuous. But hx at x is equal to 2 is h of 2 is equal to 4, which means same as the limit x approaching to 2. Hence h is continuous. Note that the function h could have been written more simply as hx is equal to x plus 2. Continuity in application. In application, discontinuity often signal the occurrence of important physical events. For example, a graph of voltage versus line from the underground cable that is accidentally cut by a worker crew at the time t is equal to t naught. The voltage drop to 0 when the line is cut immediately. Then second graph shows that the inventory versus the company restocks its warehouse to Y1 units when the inventory falls to Y0 unit. Discontinuity occurs those times when restocking occurs. Continuity of on an interval. In the previous section, we just discussed about the continuity at a point, and now we discuss about continuity on an interval. If a function f is continuous at each number in an open interval, then we say that f is continuous. If f is continuous at each number of an open interval, that means on every point of the open interval satisfy all the conditions of continuity, all the conditions of continuity, then we say that f is continuous on AB. This definition applies to infinite open interval of the form A to positive infinity, minus infinity to B, and minus infinity to positive infinity. In this case where f is continuous on minus infinity to plus infinity, we will say f is continuous everywhere. Because definition 1.51 involves a two-sided limit, that definition does not generally apply at the end point of the closed interval, but at the end point of the interval form closed A to open B, open A to closed B, open in minus infinity to closed B, or closed A to open infinity. To remove this problem, we will agree that a function is continuous at an end point of an interval if its value at the end point is equal to the appropriate one-sided limit of that end point. The function graphed in figure 1.5.4 is continuous at the right end point of the interval a, b, because limit x approaching to b negative fx is equal to fb. But it is not continuous at a left hand point because limit x approaching to a positive fx doesn't equal to f of a. In general, we will say that a function is continuous from left at c if limit x approaching to c negative fx is equal to c, and is continuous from the right at c if limit x approaching to c positive fx is equal to fc. Using this terminology, we define the continuity of a closed interval. A function is continuous on a closed interval AB if the following are satisfied. F is continuous on open interval AB and continuous from the right at A and continuous from left at B. Then we said that F is continuous on the closed interval AB. Example number 2 just satisfied. What can you say about the continuity of the function fx is equal to under root 9 minus x square? Because the natural domain of this function is the closed interval minus 3 to 3. We will need to investigate the continuity of an open interval minus 3 to 3. And at the two end point, if c is any point in the interval, then it follows the theorem. Let x approaching to c fx is equal to x approaching to c 9 minus x square, which is equal to fc, which prove that f is continuous at each point in the interval minus 3 to 3 open interval. The function is also continuous at the end point. Fx approaching to 3 negative is equal to 0, which is equal to f3, and x approaching to minus 3 positive fx 0, f of minus 3. Thus, f is continuous on the closed interval minus 3 to 3. Some properties of continuous function. Properties of continuous function means if we can add, subtract, multiply, divide two continuous function, then what will happen? If f and g are continuous, means f is also continuous at c and g is also continuous at c, then f plus g is continuous at c, f minus g is continuous at c, f into g is continuous at c, and f by g is also continuous if g of c is non-zero and has a discontinuity at c if g of c is equal to 0. That means all the functions, addition, subtraction, multiplication of two continuous function is continuous, but division of a continuous function is continuous if the denominator is not 0 at that point. And if denominator is 0, then this is the point of discontinuity of that function. We will prove part A. The remaining proof are similar. First, we consider the case g of c is equal to 0. In this case, fc by gc is undefined, so the function is discontinuous. Next, consider the case g of c is non-zero. F by g is continuous at c. We must show that limit x approaching to c fx by gx is equal to fc by gc. Since f and g are continuous at c, limit x approaching to c fx is equal to fc, limit x approaching to c is equal to gc, and limit x approaching to c fx by gx is equal to limit x approaching to c fx by limit x approaching is equal to fc by gc. Continuity of a polynomial and rational function. That means a polynomial function is continuous everywhere and a rational function is continuous at every point where a denominator is non-zero and has a discontinuity at the point where the denominator is zero. For what value of x there is a discontinuity in the graph. Y is equal to x square minus 9 divided by x square minus 5x plus 6. That means this function make a zero, where this function make a zero, all the points are the discontinuity for this, and the all the those values are the those value of x are the discontinuity make graph. Means x square minus 5x plus 6 is equal to 0 implies x is equal to 2 and x is equal to 3 are the zeros of that function yield to discontinuity. Show that mod x is continuous everywhere. Mod x is we can define at 0 is equal to 0, greater than to 0 x, less than to 0 is minus x. So this is the polynomial function which does not have any zero, and this implies that mod x is continuous function. Continuity of compositions. Continuity of composition implies that limit x approaching to c gx is equal to L, and if a function f is continuous at L, then limit x approaching to c f of gx is equal to fl. That is limit x approaching to c f of gx is equal to f limit x approaching to c gx. The equality remain valid if x approaching to c is replaced everywhere by one of the limit x approaching to c positive, c negative, limit infinity, limit minus infinity. If we have the function is continuous at c, the function is continuous at gc, then the composition is continuous. If the function is continuous everywhere and the function is continuous everywhere, the composition is continuous everywhere. So for today, this is for today's class. This is enough. So we discuss in next lecture. Have a good day.